All right, let's see if we can do another one up here. I just finished another page. I kind of phoned it in a little bit on this one. It's a pretty tough topic. All right, so right now we're kind of dealing with we did fundamental analysis on the first page. We're doing Fermilab analysis essentially on the second page. We did dimensional analysis, and dimensional analysis is going to be real important for what we do on things like De Broglie. You know, even though if you're using some of the equations I've used them for, they'll say things like in some of these things. Now it's not the right value, but it's close enough. And we're talking about something that's the conceptual model of a dimensional analysis while dealing with something like bosons. A lot of zero field. When we get to momentum of position, I can't really know it. It's a particle. You are a sphere, a circle, pi, r, pi, or 4 pi, 8 pi with spin, black hole. So you get to be at the quantum scale at those aspects of it. I am a singularity. Try to write me down. Try to write down what's going on in a black hole, and you'll find some approximations of the dimensional analysis, but it applies to analytical mechanics. I'm trying to more steps into their series of processes of phase positions, of orientation, of axioms, because axiom is going to be our spin direction, our axion particle is going to be our top spin between top and bottom on spin measurement direction in the forward position, because we want it locked out in there. We got to have a couple of axes, triangulation, not tan, but tar, tan. So Katoa, it's a triangulation according to some of the people. Physics is about circles, and triangles are circles by the easiest principles of least action and Breckenstein for, factoidal laws that need to be added into the system become analytical mechanics into these systems. So you'll see things like quadrants or states. A lot of times you'll see it in the math, especially in De Broglie or something like that. G, or we got rho, G, H is how we started it in the pressure of the pipes there as they go through. If everything is congruent here or is conserved, is constant, and it's not congruent, it's consecutive. At any rate, they mean the same thing, even if the pipes are different. The stability of the pipe is good. How we talk about this information should be okay as long as the housing on this stuff doesn't get blown over by the water pressure that blows up equally like the wind or this particle, this wave that's on a sheet, right? Because I got the high state, I got the low state, I got a positive charge, and I got a neutral charge. Not a negative charge, I got a neutral charge because these are monopoles. When we get into some of the ideas, you'll see very familiar. Let's talk about my first math equation there on De Broglie's page. I have a little bit there where it's talking about a triangulation I need to get by doing some squaring completing the square, right? And you'll see that this looks real common to stuff that I've been doing with those equations, the way those structures are set up on that page, and how the spin particle are designed. So you might do something like this inside here, squish this down, change these scales a little bit so they still fit into form on scale, alpha, beta. Wrong book. What the hell did I do with it? There we go. Scale being how these quadrants are playing out. So clearly we got a lot of that going on, and it doesn't need to be perfectly symmetrical by certain standards if you're taking some of this spin ratio, particle, black hole stuff into consideration of why it's important to say it definitely is up, down, down, down. And if you think about it, it's in here, it's up, down. It's in there, it's going to be down, up, which is going to give it some polarization, 90 degrees on a 45, right? As this changes, something else in there changes, which brings it over. Three-phase motor stuff, XYZ, XYZ. It's not too hard to see it when you're used to seeing the equations later on. That'll definitely have it. Let's see, this one will do. Yeah, sure. So I got that crap over there with the twister, the two particles, all this stuff. And arbitrarily, that's fine. Now, what he does is real smart because he starts with Z, like you want to start FMA equals G, and I'm trying to find velocity using the Broglie technique for I want to find X. I want to find AX using math to get to XA. And so this capstone first, the last page in sequence, they're in superposition with each other to these setups. Now, algebraically, methodology, Pensrose is probably going to go a lot farther faster than me, but because there's no major A set to build into here except for heavy systems to define A, and then we'll go through this, but I'm pretty sure he ends with Z function still. Let's see. Yeah, he's in the Z, but it offsets in an A three-phase kind of way. That as you're dealing with this, you're thinking about that particle on the wire, right? We're dealing with the 3D particles where I see the ring, I see kind of this teardrop thing, and in order for this to work to travel on that line, that string theory, right? You got the marshmallow over here for the stock market, right? What we're basically saying is, well, that number just doesn't arbitrarily come up, but there's nothing really causing it friction, right? There's really nothing that's saying inside of here, so this is warping, this is twisting, and by those two acting that way it acts with much less friction than the physical laws of the universe, short of these very quantum epically large and epically small galaxies and NP orders of particles and atoms and how things work at the nucleus. And so if you're observing the nucleus, you could say, I see it on scale. I see it on that N1, M2, Mn variable on what this does. And often I'll do that in the stone mill. Later on when we get into the ball and air, ball and water kind of conversational models about this, you're still going to get a lot of by science off of this. It's an NN number to M1 and M2, rho GH, rho GY, and then M and M, as those equations break down, also go to the house in the third position at NM, and they're congruent with each other. They're saying flow reduction, epically large, epically small. You're sitting here at M2, which is special relativity. Remember, special relativity is broken down n1/2. You'll see rho GH2 1/2 a lot of the times. This radiant is talking about half of this universe, half the axes on that particle are gone, or the way we generalize it in a vacuum. We have to actually change physical space through Pensrose to get the EM fields going so I can actually see what's going on in your brain. I have to turn a stone mill into a giant MRI essentially by using mathematics like this, because those fields will change like this. They'll give a signal, they'll change something, but not so much that it alpha, beta, gamma radiations you. But this conversation, Pensrose, can certainly have those effects for sure. If I catch you on that angle with it, or if I was looking for it, I'm just going to look for one prime function, some look, some sound, something that gives me a spin ratio on the time measurements of how they're functioned inside of there. So, as we pass through this here, again, so we finish that up. I did some distant, some axes differences. Here's 6 sides of it. Now you'll get I'm saving energy. I want to be conservative. And I don't want to also max out the piece of paper like you would on this bottom one, but that's the way this stacks. It stacks n1 half y f over x, n1 half rho gh, right? And it doesn't matter really which way I go about that. I can even come down. It still applies, and mathematically, that'll play to the quadrant off of this, where maybe the photon. Maybe the electron, or which order, and then you get into chemistry later on about S2 or 2S, 2P elements on that math about stuff that Chess AI programming and stuff like that. You're going to be busting up all kind of code inside here that later on. Now, for these equations, we got some other stuff I want to show you real quick before we get off Penn's Row. Beautiful. This is probably, without it doing what I normally do anyways, is about condensing all of this material on a few pages where it's right there in your face, because you can lose a lot of this. You're going to lose a lot by not seeing these things, having them on the right scales with each other, observable, working in latticed, mini-maxed kind of checkerboard percentageably. I'd see it starts to redshift out a little bit, right? So I won't be in the full quadrant. It'll just be kind of clipping it a little bit, but I can make the negotiation of 1, 2, 3 points, algebra, A plus B equals C, to tell me that that needs to be adjusted universe sandbox to the local universe. Now, like I said, this is the stone mill. There's obviously heat, light, and sound, particles, dust over in there, but we generalize with dimensional analysis those axes when there's particles getting inside here about introduction to the atom. Again, this 3D, when we're going to be getting into some heavy duty shit in terms of what this stuff is all about for electrons, free electrons, how many electron states. This can be enriched if you're down here and there's like 15 or 5 free electrons that can go into these elements and atoms. And it's pretty heavy duty stuff. It's a little bit advanced for me because I'm just looking for the base here, and I'm going to take this one hopefully until I learn it, until I memorize it, until I've mastered it. But we'll see how that plays out. This is pretty heavy duty stuff, and I'm kind of way behind on things. But at any rate here, we're just going to keep this moving real quick. Ooh, I don't want to do that. Okay, so this is Palou's occlusion here. All right, so this is going to be really important. See all the hot, cold particles we have inside here? We're saying axes fit together while they collapse. And these color ranges are going to be really important later too, not just for this, but coding this supercomputer later, this physics engine. Let's take a look. Blue, yellow, red, green, right? Now, where have you seen these things before? Okay, so there's a real big reason when you're actually doing that, the color and the numbers changes where the button's location is relative to the code, right? And those numbers are also changing some axes of what numbers these are, right? By changing some of those, it changes the motion and position of those things subtly, but I still have a general one from it. Now that I see it, I can observe it in there. I might not know its motion position. I know it's moving. I know they generally move at that speed, but I can't know for sure. And that's that 3-phase motor. I know it's moving in this direction. I don't know how fast it's moving in this direction, but the approximation of it's going to give it within here or here, -1 or +1, or I hit the electron, right? And you're going to feel it sometimes when you get into these equations and stuff. So let's keep it rolling here before I run out of time. The Euler's exclusion, and again, exclusion for principles of least action and Brickenstein. This is the kind of stuff that, while dealing with the mass gap, you can't be getting too much into this unless you design it correctly. 3-phase. It's like, if you're not doing it right to the zeta alpha function, getting paid checked at the end of it to do this, it can literally jump to whatever. So you're going to have to be pretty analytic mechanics about this to say, does it follow the steps? Am I going through the process? Can I put things into these substitutions? And if I do that, can I then put another substitution in there that still plays the same way or acts that same function as this is being manifolded, geodesic manifolding Hausdorff systems? And so again, you're gonna keep smashing them in there, referencing keys, figure out ways to get it all in there on a condensed version. Some are different than the other. So okay, so this is in a continuance on that. Now I actually did this really quickly because you'll see in one of my drawings, the 4th quadrant down, this is actually a couple of different math problems, right? Because I got the loop here and I got the loop all the way across the bottom, and I actually need to hash that out for the polarized waves. Let me do that real quick here. because we want that area under the curve on a 45. And so while we're doing that, we're to get off a little topic. Oh yeah. So remember this, because you're obviously using it a lot. The snowflake there, or the three-sided x prime, the z degree, y degree, height, whatever you want to call it, whatever it turns into. They're probably height at this point. But let's get a good wave function going. All right, so let's take a look at this. All right, so we got some issues, right? We got a high-low. This is basically a stock model. What we know, no stock number ever come off that didn't just evaporate. It's got to get X and Y from somewhere. It's got to get a timeline, and then we got to see. So that's what we know. We know that there's a timeline. It's got good times as long as they're over this line. So that's some zeta on the polarizing wave function, right? And also here we also have some directions this way as well. How do we know that? Well, not in this diagram. It's generalized 4 pi, not 8. It's in the middle. But let's watch this as we get to some of this. Now, see how there's an axis differential? So basically, as you walk around the stone mill, I see a range of things, right? See how this is now changed into a skew or a parallel where things are working and it's actually starting to expand out and things like that? Well, that's because we actually have more than one axis to consider here on the straight line. It just looks straight. You could say it's played straight off of X, and as it passes through these values, and it's actually on a curve a little bit here, but you could honestly say it's still from this Lagrange X, it's actually within the pipes on a straight line. And so what we know is this is a neutrino value, but it's also where its orientation is. So what we know is, as you get into some of this stuff, or in the first one actually, or is it this one? Let's see, hold on. Maybe we can just find it right here. And one of them I watched last night, maybe it was. I just need the simple wave. Oh, it's the other one, sorry. Do it. Come on, baby. Where is it? There she is. So as you're doing that, basically what we're saying in this lower equation is, instead of just giving it the original value of that's what it's thrown, we're actually saying it has an axis of which choice is the least. And so what that does is it kind of creates this state where we get a lot of this action happening, where I'm taking two frames and I'm putting together. I'm putting the particle A, calcium with plutonium, and I'm making 114 fluvium. As an example, this can be done other ways. It's just the one I know. Pretty heavy duty on top of this to where the particle's position is. How do I make all that stuff happen? X'd, right? Because we are dropping this down to 0 with boson type concepts. And you can't do this necessarily with, it's not going to be pure homogeneous like this with fermions. It's going to be like this with bosons, theoretical values to those particles. Where they get real close with dimensional analysis, we run the experiment, fill in the gaps. And that starts to ramp up collisions, what you can make, how often you can make that subreaction off of something actually happen. That happens all the time in the stone mill. All right, that's again finding out away from here. That box is a particle, this whole thing, and we're trying to figure out the electron position, the mass, the spin, the electron fuzz, chasing some rabbit around here by values. And this is actually pumped out by a computer, so kind of good to know. Now here I went to cryptology because again I wanted to stick with the computers a little bit. But we're going to need some of the math that I brought up, because there's a reason that this one's pretty good, actually. The numbers in themselves, they play with each other. She'll do it with somebody else's math theory with a chessboard, and high probability 8s, 6s, 4s, 2s in the corner for how chessboards move. And obviously it's talking about the center mass straight down the pipes. Like, when you get good with this stuff, you're going to start noticing it more and more and more. You might not know exactly how it plays today, especially if you're not clicking in the room. Obviously, mathematically, physics, chemistry, anything in the room where they don't have pieces of this dusted off, and hopefully with the name of the equation or you labeling that equation, make sure it's squared away. But there's a lot to check in the patent office where you have to kind of go back through all of this. Is the Penns row satisfied? Is that what we're accepting? This is pretty good. You got the Nobel Peace Prize for stuff like this, and there's a reason for it. Now he's not going to go off. He just gets paid for giving this lecture to people. Dual diagnosis. Just because you give all the kids the thing once and get it doesn't mean that it's going to work forever. After your tweets come out of your face equation, there's going to be another group of kids coming in here, and they'll need it again. And practice until the neural net on there has no reason to evolve, and you even remember when to emphasize things and put special equations in there yourself about crap. And sure. So anything else we got in here? Okay, yeah. So this is the how do you do a physics engine. And again, I just wanted to be very clear with the colors, the concepts. This is very small, this physics engine. Now, what I think he gets out here is, a couple of shots out of things, and he's going through it. But basically, he does one real quick, where like he's doing all this for 15 minutes to get a ball, some other things, get it on the board, make sure it's there, and then let's see if I find it. Is this it?
Perfectly fine.
Yeah, there, and that's what it did.
And you can
experiment
with this quite a bit. So, for example, we could set our...
and there's some real things about this. Remember, we're stretching out energy into ones and zeros. Just particle 2, particle 1. It is N1 half a lot of the times in that three-phase motor bit. And so when you get that, you get a button. What is a button? A button is a toggle. A toggle is a switch. They're all Z's, they're all ones, and they're primes. Sometimes they're relative to each other, and in order for this thing to work, not only does there have to be a charge to that light, but it also has to go through everything else in here. Otherwise, stuff acts funny. And then the physics engine that I program, if I didn't get that apple that I threw in the ball in the examples, if I don't get it off the ground, doesn't matter. It's on gravity. So you could say the atmosphere pressure is 0 or 1 or something like that in the house close to the ground. But when you go shooting that apple, if you're not 5 or 6 feet off the ground like the human body would be, when you program that into the physics engine, what it'll do, it'll glitch out. It'll shoot it through the wall. Doomslayer will be stuck inside of there. 100% Ultra Nightmare Lucy. You're gonna need to get in here and pull the strings of fate around a little bit to get the geometry lined up just right to get it back in there and have that debug. Now, it's easy when you're debugging 42 over here or breadboard. This is something where you have to be very good about the analyses and functions that you put in. But in the end, that's filling out this program. Z to the top. It's got to have the bottom limit of the first word and the end of the first section. And 0 was its start, 1 was the end, and we're starting in Z. The first letter of the last function has to be based in those R2s, R3s. We're talking about the axis of what physical position on Earth was it, how is it orientated, and all that other stuff that you get in here to twister theory. Again, Penns row, you sweetheart. Or here, this probably Bernoulli. Definitely got a lot to do with it. But you'll see laser beams, right? This just doesn't work. You can't just amp that thing up. If the wave functions had a pipe in it that bent too much, then this is going to create a collision. And on the inverse of that, if it's too slow and you're straight, it won't allow this machine to work. So changing out parts of Fermilab, certain rings, certain distances, the amounts of elements that you have in there, the things and the axioms that change when they're talking about a dark matter particle that is an axion, that is an anti-photon. When I'm looking at the reaction, it should have been heat, light, and sound. It should have been. For whatever reason, it didn't. Now, the reaction still happened. It's physics. It's on that y to zeta to y axis. But in there, you could quantify that as that. If you recognize that experiment, you might be able to figure out some mathematics trick that'll get you there. They all do it. They're all antiphotons. They're all supposed to do physics, whatever result in the chemistry experiment when you pour it on here. But it does this because that is that X, Y, and Z. Always X right here. X, 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 X to the 0 or prime, and then X degree, but it's also XYZ. It's also XYZ, XYZ, so on and so forth. And you get a lot of that pattern stacking, infinite circles or spirals or strings inside of here that tie it all together, keep a pressure on everybody. So anything else I got left in here? I think I covered it. I hope you like where this is going. And like I said, sometimes from original orientation, you'll find that there has to be some standard models to certain sets. And if you look at the position of how many 9 balls I have in here, but there's actually 8, but you could call them 10. You could say that there's 7. In a way that there's only 6. 3, 2, 1, you can backtrack it and say they independently stand on their own, but as a group or a set in some cases, if I wanted to be divergent, F1 plus F2 equals minus F1, by grouping those concepts, they'll basically apply like that function will with some cross section, right? We want to deal with the axis underneath there that is the particle, where we want to observe this and save our energy, so that way we're not saying, well, it's everything in the universe in Fermilab. Something happened here, it let out the fuzzles. That goes against physics, which is physics. The fact that it did, and I know it did inside of there, is still the physics. Let's see if we can get anything, connections over here,
Here we have
or connections over here, but we're not sure which one is which yet, right? We just know that there might be a problem from this end into it, or it couldn't send them out for some reason on there for signals. And again, you are a circle, so inside here it's something that you have to get used to, at least. Hope you like it so far. Catch you on the next one. So Pensrow next, because we'll be getting into a lot of this. Obviously you've seen it. There was some big inspiration. See some of the functions that go into this. And of course this mathematic plays outstanding. Golden ratio here, whatever he's calling it, really doesn't matter as long as you're on track with it. I mean, it matters Pensrow, but for most common mathematicians or assholes that don't know any better, you can get away with some stuff. Remember, if you do that, it doesn't really matter. We could save that. We could change this value of the equation and know this one, or know this one, but guess this one. So when we have that standard model, what do we know we have? What do we know we have inside of the set that observes that value? And then I can, graph it down, put a to this snowflake, put down the graphing steps that are actually necessary, because these are the vector positions. This is the visual geometry, and this is the parapsychology paradoctorate there in literature and things like that, as you're writing out the steps. What is X? Well, X is this. What is Y? Y is this. What is Z? Z is this. When I go programming in those vectors there with these types of constants, it's not just any regular old X, Y, or marshmallow, you know what I mean? It's this marshmallow with these kinds of points on price, percentage up or down, and volume. Sure, in the gradient Laplicant A to A changes, so PT test, I got age, height, weight, or whatever combination of those values change the axiom some way mathematically by analytic, fundamental failure proof missionary position in here. And get used, lock your feet, demon core, because you get too far out of there, we're out of those types of thinking. Fermilab, remember, overdone it. Every axiom past this point, it did a thing. Now they're chasing the mu, right? Because that was one of those take a step back or build forward through. Probably they're on a bit of both with the twister theory there, measurements of spin direction, right? And then really get into it with those concepts. So I'm burning up some time here. Catch you on the next one.